Yeah,
Hello everyone. So I'm Ashutosh and I'm assistant professor at CSC Department IIT Kanpur, and I would like to welcome you all again to the second day of SAIL. And I hope everyone has been enjoying the talks, and you had good time yesterday. There were a lot of interesting talks yesterday. So before I start, one small logistical thing. During the session, if you have any questions for the speaker, please type your questions in the QA window and don't type anything in the chat. And we will be taking all the questions towards the end of the talk. All right, so maybe let's get started. So for this session, it's an honor to welcome Mr. Sachin Kumar. So Mr. Kumar is a senior data scientist with LexisNexis in the US. In there, he works on research and implementation of novel deep learning and machine learning techniques to solve various downstream NLP tasks in the legal domain. At his work, he has championed initiatives like query intent and question answering, which have been rolled out in various products of LexisNexis. And today he's going to talk about a very interesting and relevant topic on question answering systems for the legal domain. So without further ado, I would like to give the stage to Mr. Sachin Kumar. Please take it away.
yeah. Thanks, Ashutosh, for this great intro. And it has been a great pleasure actually to present here at the sale. So, as Ashutosh mentioned, the topic that I'll be presenting today is the question answering system for legal domain. So, just to give like a high level introduction to the agenda, the topics that I'll be walking through was mainly like the introduction, a brief introduction about LexisNexis, what kind of question and answer systems exist, and what are the different types of implementations which are there, and the knowledge-based QA systems, their introduction, like the implementation in legal domain, how we did it in here in LexisNexis, and other type of QA systems or information retrieval-based systems. Brief introduction about that, implementation in the legal domain. So we'll be covering a lot of the theoretical aspect as well as the implementation aspect, mainly with the algorithmic part and like high level flow or view of like how we had implemented here in LexisNexis. So uh, feel free to post your questions. I'll be taking it into the presentation. So that get started. So just like I will start with a high level introduction to the LexisNexis. So some of you might know LexisNexis as a legal research product that helps the legal practitioners with various aspects or various steps of legal research process. And we do have a global presence serving US, Canada, South Africa, India, Australia, UK, and we do have various products like Lexis Advance, Lexis Pass, Shepherd, StateNet. So these are like a high-level introduction, what my company is providing or being like a provider of the legal research to the various legal research practitioners. So, diving into the topic of this talk, question answering systems. So, the people who are not aware of what question answering systems are, so just a simplistic representation of that. A question answering system is anything that accepts any input in form of natural language and gives you some kind of an answer. So, on day-to-day basis, you might have used some of the question answering systems like voice assistants, like you might have used Alexa, Siri, or you might have interacted with chatbots, or like definitely you might have asked any question or like any kind of question in Google, and you observed like an answer presented in front of you, like as you can see in this particular figure. So these are the different forms, like how you see the question answering systems on day-to-day basis. So the question answering systems that I'll be talking about today are something that basically closely aligns with what you see here, like in the document search results, where you ask a particular natural language question and get an answer back.
Sachin, so I think so attendees are saying that your voice is a bit low and it's also kind of breaking. So I don't know some.
Okay. So okay. So let me try it again. So is my voice audible now?
Yeah, now it's much better actually.
Okay, so something might be wrong with my headphones.
Yeah.
So yeah, so I was talking about the question answering systems. So you might have interacted with some question answering systems on day-to-day basis, where it basically accepts an input in form of a natural language. It outputs a concise answer. So it can be voice assistants like Alexa, Siri, chatbots, or the document search results as you've seen in the Google. So the question answering system that I'll be talking about today is something that you might have interacted with Google, like you ask about a certain question and in your search results, you get an answer along with the search results. So before actually starting with the theoretical aspects or of the various systems we have, I'll start with and like what is basically the need for the question answering for legal domain. So I'll take an example of LexisNexis legal research platform. Like on an average, we handle around 1 million queries per day and used mainly by the attorneys or various legal researchers. It can be frustrating sometimes when you are actually, like for example, if you're starting out in legal research, like you're fresh out of the law school and you didn't had like a lot of context or guidance to search in the to do the legal research. And some of you might be aware about the fact like mostly the legal researchers do their legal research with the Boolean queries. So someone that is starting out in legal research, Boolean queries is not quite their forte. So they might not be able to craft the correct Boolean queries, or they might not be having like correct context or what thing to actually search for. So question answering provides you some set of answers that let you get started, gives you some legal concepts as you notice in the answers. So that will help you get started and that will help guide your legal research to further refine it. Other thing was when you're searching, the query intent is not something very understood. Like when you're searching for the search results, and you will get like all kind of search results which might not be relevant to the question you are asking. And you have to, when you're like looking for certain specific fact or certain specific number, you might not be able to get it at the first glance, and you have to go to many search results to find the answer. To illustrate this point, I'll just give like one example with that. Like for example, you search for a particular legal question like, what are the elements of mail fraud? So as you can see, the answer will be something very straight and concise, like elements of mail fraud are this. And elements are something like, in US law, elements are something, there are certain points that you have to prove in order for the court to deem a particular person as guilty of that particular thing. So a short and concise answer would look something like this. But if you are scrolling through the document search results, like for example, in the case of Lexis Advance, you might be getting a lot of documents, which are basically the cases, decisions, and something facts related to cases. So you have to navigate and gather around facts from various cases. So that is something very time consuming, and you are not getting actually the facts pertaining to your question. So that's how actually, so that is just to illustrate my point, why the question answering is something that is really required for the legal domain. Because in legal research, in many places, or in many instances, you might be looking for certain specific facts or numbers. That is something not conveyed when you are when you're looking in certain cases. So getting some answers for that question might actually be pertinent in most of the cases. So on a high level, there mainly two type of systems exist when we talk about question answering. Firstly is knowledge-based QA systems, where you map the question to certain predefined structured entities and you retrieve answers from a database where you do have a certain pre-canned answer stored for those. Another type of systems can be information retrieval based QA systems, which is not as rigid as you might observe in a knowledge based QA systems. And there you don't have like a pre-canned answers, so you retrieve some potential answers, and you can re-rank it to get some top K answers relevant to the question you asked. So next, I'll start with the implementation of the knowledge-based QA systems. So this implementation is something that we had implemented in LexisNexis. And so in LexisNexis, you get a answer card on top of your search results. So this is an answer card just like you see in the Google. Like for example, you search for a particular question, you get an answer card on top of the document search results. So the only difference here is we have implemented it for certain factoid questions. So when so this is something how it operates like user enters a particular query. We identify the intent of the question, target of the question. We look into the answers database where we have pre-canned answers stored, and we present the answer card along with the search results. So as you might have noticed here, I mentioned question intent and target term in order to retrieve an answer, a pre-canned answer from answers database. So, and yeah, this is just something like, how it looks like. You search for a particular question, and so in Texas, what is the prescriptive period of breach of contract? So prescriptive period is basically a statute of limitations, and you ask for breach of contract. So you get an answer card along with search results. And as I mentioned, we identify the intent and target term in order to retrieve the answer card for question asked. So intent is the question type, and that can be statute of limitations, that can be definition, elements, doctrines, burden of proof, jurisdiction, judges, experts. So these are something which are very limited. So this is like one of the limitation of this knowledge with QA system. There are certain type of questions we answer, and once we identify the question type, another thing that we identify is the target terms. What specific legal term that question was asked about? Like for example, as you see in this particular question, in Texas, what is the prescriptive period of breach of contract? So Texas is jurisdiction. Prescriptive period is the question type or intent, and breach of contract is the legal term or target terms. So for this particular question, once we identify the intent, prescriptive period, which is basically the statute of limitation, and breach of contract target terms, then we will be having a pre-canned answer stored for statute of limitation or target terms. So we retrieve that and present it as an answer card, as you can see here. So here we identified the statute of limitation as an query intent, and target of that query is a breach of contract. And we retrieve from our knowledge base the answer for that, and we present it along with the document search results. So this is an implementation for the knowledge-based QA system I was talking about. So I'll discuss some more details about like how we identify the intent and target terms. So for this particular process, we do the data annotation. And as part of the data annotation process, we identify the intent of the query and target of the query for various question types. And we do the IOB tagging. So IOB tagging, as you can see, like statute of limitation of derivative claims. So it will be BSOL, ISOL. ISOL is tags. O is the tag that we are not relevant for, that is not relevant to our exercise. And derivative claims would be tagged with B target term, I target term. So for our model or our machine learning pipeline for the identifying the intended target terms is something that looks like this. So we have raw data, we transform it into features, which can be word-to-vec features or various word level features like OSTAG, lemma, unigrams, bigrams, and use the machine learning model, mainly as the conditional random fields. And that model, what it does is it predicts the tags for every token in the query. And those tags will be intent, target terms, and jurisdictions. So this is the knowledge-based system implementation that we had implemented in the LexisNexis platform. But there are certain limitations associated with it. So first one was it was limited to the factoid questions. So factoid questions were something like, it is something kind of a fact that exists. And mainly it's limited to as I mentioned about the query intents, like statutory limitation, definitions, elements, doctrines, judge. So these are the sample queries as it appears to you. So these are the only questions that can be answered with this knowledge-based system. Other thing was the retrieval of answers are here dependent on the correct intent and target terms identification. So in a certain query, if I was not able to identify the correct intent and target terms, then I won't be able to deliver the correct answer card for that. And another limitation is because we are presenting a pre-canned answer. So it is limited to like whatever number of answer cards are stored there. So like, for example, for a particular intent and target term, we identified, but there is no answer card stored. We won't be able to deliver an answer card for that. Besides that, so those are not the only questions which can be which can be asked by user. So the questions can be procedural. Those can be analytical type of questions. It can be questions about a certain rule or statutes or multi-topic questions. So those are the answers which are not addressed by this particular system. And in order to update the system, we constantly need to update our answers database to expand on the various type of answer cards we answer. So these were the limitations of the knowledge-based system. In order to overcome that, we moved on to the other type of systems, which were information retrieval-based systems. So on a high level, information retrieval-based system, how it operates is you have a retrieval step where you have a certain set of documents stored, and you'll retrieve some top K documents out of it. And out of those top K documents, you will re-rank them and get the potential top K answers. So this is the premise for the information retrieval-based systems, how they operate. Now, in the information retrieval-based systems, searches can be done like, lexical way or semantic way. So your lexical search can be something like BM25 or MLT functions, or more like this function in Elasticsearch or Solr for getting the relevant documents. So in the lexical search, the primary focus is on the matches of query words and their variants. So the contextual meaning is something that is overlooked from the lexical search aspect. And in order to address that, or in order to accommodate the contextual meaning of the words, you can do the semantic search. So in semantic search, we understand the intent or contextual meanings of the word as they appear in query. And this is a dense representation as compared to the sparse representation of the lexical search. And the semantic search, you can do like either with word embeddings like glove or word2vec. But the problem with the glove or word2vec is if you have some out of vocabulary words, then those won't be addressed. And it is not sensitive to context. Like, for example, if I say a sentence like, I went to bank, a river bank for fishing, or I went to bank for transaction. In both those sentences, bank will have same embedding because it's not sensitive to context. But if you, as a human, you see like those sentences are not something same and basically mentioning altogether different context. So that is a limitation if you're using the glove or word2vec for semantic searches. And in order to address that, there is another way to do the semantic searches, like BERT embeddings. So in BERT, it is trained on the sub-word level. So that is the reason it avoids the out of vocabulary searches, and it's sensitive to context. So as I mentioned in my earlier example, like I went to bank to make a transaction, or I went to river bank to do phishing. So the bank there will be having different embeddings because the BERT embeddings is context sensitive. So it will accommodate context when you present, like, so it's not dependent on dependent on like, it's not do the embedding just like the word embeddings, and it is something that accommodates context. So those are on the high level. If you have to do the retrieval, those are the two different type of indexes you can implement. Like it can be lexical search or semantic search. So I'll start first with the lexical search, or which is basically implemented with the BM25 algorithm. So if you know about the TF-IDF algorithm, so TF-IDF, just to give a brief intro, it's term frequency inverse document frequency, where you identify as how a certain phrase or word appear in a certain document and the relative importance of that word across different documents with IDF function. But it does have certain limitations associated with it, which are further improved in BM25 algorithm. Because BM25 is derived from the probabilistic approaches, it basically dampens the impact of term frequency in the term frequency function, and IDF function gives a negative score for terms with very high document frequency, so that the a particular term which does appear in a particular large number in the certain number of documents, that won't overpower the search results. And it also accounts for document length, so that there are not certain longer documents or outlier kind of documents overpower the searches because of a certain term appearing a lot in number. And BM25, when you index it, it's an inverted index. Like, for example, as you can see, this particular document, like, all the defendants argued that because victims don't. So there are certain terms appear in there, and those terms can be like a document number 2 at position 3, document number 4 position 7. So that's how it arranges it. And when you search for a particular query, it looks for the document and their associated position in order to present you. So it basically looking in the term and their appearance in the document in order to give you the search results. So as you can see, because it's dependent on the term, so their appearance in a certain number of documents, it's not sensitive to context. So that is how the limitations of lexical search comes into existence. So as I mentioned, there are certain limitations associated with the BM25. So there is a need to move on to vector-based search. So because BM25 searches are not good in the out of vocabulary searches, and vector-based searches just provide better semantic query understanding, and it will help you understand different meanings of a particular word or phrases in the query. So, like, for example, as you can see on the left-hand side, there is a particular question asked, like, how long does a canned soda last? So canned soda can be referred to by different terms, like soft drinks, unopened pop, carbonated drinks. So those all are different words or phrases. So if you have to happen to use the vector-based search, there it will actually identify the different representations of those words. But if you have to use in BM25, you have to use a certain dictionary to do the query expansion or provide, which will be storing actually different meanings of certain words or phrases. So that is kind of an extra work. And because you have to do the extra work, it is rigid or not flexible enough, because it will be doing the query expansion as per the dictionary or mappings you provide. So that is not a scalable approach if you have to do like on a million documents with like lots of complexity, like as you can see in the legal vocabulary, there are different terms or different phases. So there's no good way actually you can do the good query expansion for all the legal words and phrases. So that is like one of the reason the vector-based search is like produce more relevant results as compared to BM25. Another reason being as you can see in the right-hand side. So semantic retrieval, you also get the relations between different words or phrases mentioned in the query. Like for example, you have a query like hotel on a beach. So hotel is located at beach, and you have like different documents like hotel is on beach, hotel is in Germany, hotel gets 5 stars. So like document 1, document 2 does mention location of hotel. So with a vector-based search, it will be able to understand the relationship between those words and in what context they were mentioned. So those are represented as like more relevant documents as compared to the document 3, which is mentioning one property of hotel, but does not mention the location of the hotel that the question is asking about. So this is just to illustrate the point why the vector-based search is more important, and how it does helps us to understand the deeper meaning or semantic meaning of the question being asked. So in vector-based search, as I mentioned in the BM25, it's just like a modified version of TF-IDF. So that's how we measure like which documents are relevant by measuring the terms of relative importance. But how we identify the documents presented are relevant to the question asked. So in vector-based search, we create the query vector and document vector, and you can use the certain similarity measure like cosine similarity, or it can be Euclidean distance, in order to find the nearest document vector to the query vector in order to get the relevant documents. But if you have to do it on scale, the vector-based search there are certain challenges associated with it. Like for example, starting with the BM25 search engines, there is support available in Lucene. So Lucene is a library which does help you provide the capability to index large number of documents and do the BM25 or use BM25 search algorithm on top of it to get the relevant documents. So there it computes the modified TF-IDF score and gives you the sparse vector representation in order to get the relevant scores. But you have to do the dense vector-based search. Lucene does not have a capability for those, and it does not provide you the capability to store the query documents using dense vectors. And the inverted index that is there in the Lucene is not optimized for the vector matching and scoring. So an alternative, or like how we overcome this challenge with the vector-based search, is the ANN algorithms. So ANN is approximate nearest neighbors algorithm. It approximates the similarity and provides you with the similarity scores. So why we use ANN algorithms? We can do just the nearest neighbor between query and document pairs, or like with the document corpus. That is something it can do, but if you scale up the number of documents, you have to do the it will scale up polynomially with the number of as the number of documents grow. So that is computationally really expensive and a very slow process if you have to do for, let's say, 1 million documents. So that is not a feasible thing if you have to do the vector-based retrieval for a large number of documents. So that's why the ANN algorithms comes into picture. It is faster and with some trade-off of accuracy, because you are approximating the similarity. And I will move on to the next part. So approximate nearest neighbors algorithm, how it speeds up the search is it does some vector transformation, and it encodes a vector in the indexes using various data structures like trees, latent semantic hashing, quantization to encode vectors into more compact form. And it does the non-exhaustive search using techniques like inverted files and neighborhood graphs algorithms. So those are the steps involved in the ANN algorithms, which speeds up the process of vector matching. And these are the ANN libraries. If you happen to implement the vector-based search, these are the libraries you can use, like a FIAS library developed by Facebook. So that uses the LSH and HNSW algorithms to index the and provides a faster vector-based retrieval search process. And it is a really good technique, but it does not actually perform on in benchmarks as on par with the other library called NMSLib. So NMSLib library is based on the data structure, or the algorithm called HNSW, hierarchical navigable small world graphs. So in hierarchical, it basically builds up, uses the graph data structure and uses the greedy algorithm to find the shortest path to the nearest nodes. And just like in high level introduction, it builds like multiple graphs. Like on the top level, there will be like fewer points or fewer nodes. And as you moved like to the other layers, there will be like a lot of points, or you moved on to finer details. And your search will terminate once you have like minimum number of nodes or a cap of the nearest neighbors you want to like restrict it to. So that's how it finds the nearest neighbors, or the vectors which are more closely aligning with the query vectors. And this is just like a cheat sheet I was able to find if you happen to experiment with the ANN libraries for your vector-based search. So this can be like in high level workflow or flowchart, like you can use like exact nearest neighbor search, and based on the GPU limitations, or based on the uh, like the scale of parameters you are dealing with, you can actually use like FIAS library or NMSLib library, or the other various other libraries exist. So it will provide you like kind of like a workflow, or a decision process in order to navigate the workflow or experiment among different libraries available for your vector-based search. So I will move on with that to the IR-based QA system implementation that we did here at Lexis. So in our implementation, we had primarily two components. The one was like an online module where we were retrieving answers using sparse or BM25 based searches and dense vector-based search retrieval methods, and the factoid-based answer cards that I mentioned in the knowledge-based systems. And once we retrieve that, we re-rank them to get the final answer set. And there's an offline module associated where we create the BM25 index and vector index, for which we are using the NMSLib library, as I did mention in the earlier slides. So this was the system architecture for the IR-based QA system we implemented. So as you can see, the navigation part is a user asks a particular question, and for that particular question, we retrieve the answers from our knowledge base, which is factoid answer cards, a pre-canned set of answers, as I mentioned in the knowledge-based QA system. And the other one will be BM25 index, and the another source will be the NMSLib based vector index. So why we are combining the sparse and dense vector index is vector-based searches does also have certain limitations associated with, or there are certain kind of documents or queries where you will get like better results from the BM25 index as compared to the vector index. So this hybrid approach does provide us the capability to use the best of both worlds, because once we retrieve the answers from the factoid cards, BM25 and NMSLib based index, we re-rank it. So we do have a re-ranker model with which we re-rank it in order to get the answers. And as you can see, for the vector representation, we are using a legal BERT that we did train in-house, because the BERT model that are available, like the vanilla implementation that is available in the market, Those are not something actually accustomed or seen the legal training, legal data. So that's why we pre-trained our own legal BERT that we use in order to create the vector index. That is something how we encode our question to do the vector-based retrievals. And in the offline module, we have a legal documents corpus, which is encoded, which is segmented into which is segmented into the passages. And those passages are something that is encoded with the legal BERT and stored in the NMSLib-based vector index. And the answers, as you can see, this answers block. So these answers won't be span-based answers. These will be passages answers, basically. So because we are storing the passages and this re-ranker after the retrieval from all three sources, we re-rank it in order to get the top passages or top potential answers. So in the IR-based QA system, as I talked about, there are key components involved in there. So the first is legal documents corpus. So as you can see, the legal docs corpus used in the offline module. So there we had 100 million passages drawn from US case law, US case law key passages and head notes. And for the answer sources, as I mentioned, it had dense retrieval method, which was an MSLib index, sparse retrieval method, which is BM25, and factoids database. And for the legal BERT, as I mentioned, the legal BERT used here in the online or offline module. So that is something that we pre-trained in-house on US case law key passages, including head notes. And also to add further context to it, we also fine-tuned it with the Siamese technique. So what Siamese technique does is it trains it it fine-tunes it for the sentence textual similarity task. So that basically helped us in our experiments to provide better results as compared to just using the pre-trained BERT. And for the re-ranker module that is mentioned here in the online system, so we actually trained a BERT-based binary classifier on the question answer pairs. So we do had annotated legal question answer pairs that is something that we sourced across our organization. And in order to improve the generalization of our re-ranker, we also added the Google's NQ data set that will actually generalize to a non-legal type of context. So that's how our re-ranker is trained. So this is just how it looks like. So this is the QA system we had. So like, for example, you search for a particular question like, are emotional damages recoverable in a discrimination suit under Title VII? So you will get certain passages as answers, and you can click on those links in order to read it in context, the context around it. So this will provide you like a short and crisp answer, but you can read it in context after clicking on that particular document to see all the passages around it. So moving on to the evaluation of the system. So we did created a goal set, which were like quite comprehensive and covered like various question types, like questions related to rules or statutes, single topic questions, like, where there's single legal topic involved there, multi-topic questions or analytical questions where you're asking about certain number in that particular question. And there are various other question types around, like we did evaluated across multiple aspects around 15 to 20 different question types. And how the SMEs evaluated was it was on the scale of 0 to 3, like 3 being most relevant, and like 2 it's partially answer it, 1. So that's how like it was arranged. And because it was a retrieval based system and we were presenting multiple answers, so we used DCG, or discounted cumulative gain, as the primary evaluation metric. So this was the overview of the system I was mentioning about, and we are still working on this IR-based QA system. And like right now, we had implemented it for US case law and treatises secondary content, but we are expanding the coverage of the our IR-based QA system, like expanding on statutes and the other content that we have still not exposed it via the system. And we are working on various aspects like improving the speed and lowering down the costs and matrix for that. So because we are using a vector-based system, so while we are serving in production, so obviously in order to maintain the bird-based model and those vector indexes, it is really expensive thing. So, but we had worked around different initiatives or different projects actually to lower down the footprint of the models and compressing those models. So those are something that are a work in progress. And lastly, I will acknowledge the team that is primarily composed of data scientists, product engineers, and product people, and subject matter experts that help us deliver those systems. So with that, I will open the floor to questions. Thank
Okay,
you.
thanks a lot. Yeah, it was a very interesting talk. Thanks for the insights about your existing system. So maybe let's move to questions. So there's one question from Rajeshwari. So she's saying, do you consider the temporal aspect when you retrieve the answer? Do you do any ranking of the answers?
So yeah, we so after retrieving the answers, we do apply many filters. So those filters can be jurisdiction filters and time filters as well. So like for example, if we presented an answer, but that a particular answer, but the case from which it was derived from, so that case might have been overruled. So now it is not actually relevant. So that won't be like a good answer for that. So we do have like time filters for that, and we do also deal with or like see if that case is something that we're presenting answer from is not actually overruled. So that should be a valid answer, and there is a temporal aspect associated with it, which we apply as an kind of like internally as a filter for in the retrieval task.
Okay. Yeah, thanks. So then she has another question. So does your IR-based system handle word sense disambiguation and anaphora?
So with word sensitive disambiguation, I guess you are mentioning or you mentioning like if that particular legal term or word is mentioned in another context as compared to what context the question was addressed for.
Yeah, I think so. That's what she means, I guess.
Okay. So for the word sensitive disambiguation, we don't have like any specific module associated with it does that, but like how we trained our model and how our re-ranker that see that thing. So that basically takes care of that and handles it pretty well, because as I mentioned in the so we had pre-trained our BERT model, but we also fine-tuned it with Siamese technique with like lots of like textual similarity tasks. So that basically implicitly handles the word sense disambiguation or the context that particular legal term is mentioned. Like that particular legal term can be mentioned like so it can altogether actually change the context you ask the question. So it can be like an analytical question or it can be procedural question depending upon the context. So our like multi-tiered approach does handles it implicitly.
Yeah, so maybe just a follow-up question on that, which it's more from my side. So since these are legal documents, do you really come across words which are kind of ambiguous? Because I mean, words and terms would be very concretely defined, right, in legal documents?
Yeah, so legal documents actually we can have the disambiguation thing. So it can happen actually where certain questions are kind of like on boundary value. So boundary conditions. So like, for example, a certain question, can be analytical question also, or can be procedural question also. It depends on like how you interpret it. So depending upon the context provided, so I will say there won't be like, lots of questions around that, but if you consider the boundary values where you can have like, a same question overlapping across a multiple question types, so that is a possibility.
I see. And do you also face the problem of anaphora in legal documents?
So anaphora, you might need to provide some context, like
So anaphora is like these can be. So for just to give an example, you might have a pronoun referring to some kind of a noun, or maybe some kind of a referent to an original entity. So these kind of things, do you come across in legal documents?
So yeah, that can be a possibility because legal vocabulary is quite extensive, and you won't believe actually there are certain terms which does appear like, in the normal terms, but those can be legal terms as well. Like, for example, I'm falling short of remembering a good example, but I've seen some examples which like, in a normal context, if you don't have to mention like, it is like a legal question, you might like, consider it as like, it's not something legal. But when you see the legal corpus, like, it can be something referring to a certain aspect. So those are the things actually we did notice also in our SME evaluations, because like how our model interpreted those things and how SME sees it from their domain knowledge, those can be different. So there is like a underlying complexity, and especially in the US system, the law is quite extensive and various branches are involved in there. So uh, I'm sorry, but I don't remember the good example for that, but that thing is a possibility. Not a lot, but it's possible.
Okay. Okay, so Nishit has a question. How is the system handling causal relationships?
Causal relationships, I guess you are mentioning by causal relationships, you are referring to if like, a certain concept is like, certain implication of concept is mentioned. So those are, a certain kind of a questions as we see. And those are something that is also included in our evaluation, like how when we evaluate the question answering system. And in our training system, in our training corpus, we do have like, all those kind of documents or those kind of passages which does capture a good relationship between the legal concepts and their implications. So I will say across our like, various techniques or like multi-tier techniques in the retrieval and the re-ranking phase, that basically takes care of those causal relationships, because that's how actually is there in our documents or the training data that we use in our legal BERT or re-ranker. So I can say it's, it's implicitly handled in our system. We don't have like any specific module looking for those relationships, but our re-ranker and our retrieval system takes care of that in our semantic search.
Okay. So there is one question from Janardhan. Do you take care of amendments to legal documents?
Yeah, so in our system, in our Lexis ecosystem, we do have a service called Shepherd-Eyes. So which Shepherd-Eyes actually, if the certain system has certain amendments introduced or it is overruled, so that is something we introduce. We also include that particular aspect in our retrieval process. And we also have like, a data enrichment pipeline which runs on regular basis, like daily, which basically create the index again, or update our like, entire vector based index with the new delta created, or the new amendment or new data that is generated for any case or any aspect of the legal system.
Okay, so there was one question on, so in BERT, we have this limitation of 512 tokens, right? So, I mean, how do you handle that basically?
So as we have seen, like in our, so as I mentioned, okay, let me go back. So as I mentioned, like, we are segmenting our documents in passages, and we are encoding those passages with legal BERT. So as we seen, like, in our passages, on an average, like almost like 95% or 96% of times, just using the like a 128 token length sufficed. So we actually cap it up to the 128 tokens, and we didn't use actually up to the 512 tokens, because that made the model actually uh, quite huge, and that training task was taking like too much of time. So as we did notice, actually for 95% of times, just using the 128 token length was sufficient. So just like 5% of times, like, we need to exceed or go beyond the 128 tokens length. So we did use just the that particular length, as we noticed in our analysis, like, that's how the length of passages go.
Mm-hmm. Yeah. So you, I mean, like you don't use some kind of hierarchical architecture, right? Like, for example, you might break. So I mean, recently in one of our works, what we did was that for legal documents, these are very long. So what we did was like we divide it into chunks and then get the representation for each of the chunks, and then those representation become input for the next layer of, I mean, next level of BERT, and then you get representations from those as well.
Yeah, so in our the data enrichment pipeline or the offline module, when we build the vector index, so there we also do that thing with various data pipelines where we segment the document. So we have like a parser written for those, which basically segments the document into multiple passages. And for majority of the training task, it is 128 tokens length, and I guess for a certain component, a certain like portion of the training, as you were mentioning, like using the 512 tokens. So we don't use like 500 tokens or 12 tokens. For majority of training is 128 tokens, but for some part of the training it is 512.
Okay. Okay. Thanks a lot. I think we are done with the questions. There are no other questions now, or maybe just so one. Yeah, one last question. Legal BERT is pre-trained on case law and statutory document. Is it also has custom vocabulary? Does it?
Great question. So we do use our custom vocabulary, and we also modified our to create our own tokenizer as well, because the normal tokenizer does not handle the citations well. And in the legal documents, you might notice, like, there are lots of legal citations referring to various statutes or RFCs. So we do use our custom vocabulary, and we do created our own tokenizer, like a modified version of
Okay. Okay, so I think we are done with the questions. Okay, thanks a lot. I mean, thanks for giving a wonderful talk and telling us about the inner workings of your system. And I would also like to thank all the attendees for attending the talk. So now we are going to switch to a